This week, Google found a way to make small AIs earn their intelligence using a bizarre new training method that mixes two systems that were never meant to work together. And while that's happening, another Google team quietly built an AI scientist that cracked a decade-old biological mystery, one that took human researchers 10 years to solve. And it did it in just a few days. Let's start with the first one because this might be Google's smartest training trick yet. A team from Google Cloud AI Research and UCLA released a new framework called Supervised Reinforcement Learning, or SRL. And yeah, the name sounds weird. Supervised and reinforcement in the same sentence because those are usually opposites. In supervised learning, the model is basically told the right answers up front. In reinforcement learning, though, it has to figure them out by trying things and getting rewarded when it's right. Google's twist is that SRL gives the model the right answers, but still makes it earn them through rewards. Kind of like giving a student a solution key, but still making them solve each step to prove they understand it. It sounds contradictory, yet it works brilliantly, and that's what makes it genius. The whole problem they're tackling is simple. Small models like qwen 57B instruct collapse on hard problems. Give them a math challenge from the S1K1. One benchmark, and they start hallucinating. Even if you feed them perfect teacher examples, normal supervised fine-tuning just makes them mimic token by token. Long sequences, small dataset, about 1,000 examples and final scores actually drop below the base model. So the researchers asked, how can a 7 billion parameter model learn to solve a problem instead of imitate it? Their answer, SRL. It keeps the reinforcement learning structure but injects supervision into the reward channel instead of the loss. Each expert solution is broken into smaller steps called expert trajectories. For every prefix in that sequence, the model generates a hidden reasoning section wrapped in think tags. Basically, it's private scratchpad. Then outputs one single action. That action is compared with the teachers using a string similarity metric from diff, and it gets an immediate reward score. The difference here is massive. The reward is dense. Every step gives feedback even if the final answer is wrong. The model learns which decisions matter without being forced to copy the teacher's text. And the numbers prove it. All tests were done on qwen 57 billion instruct using the same deepseek R1 formatted S1K1, one dataset. Baseline scores were AMC 2350, 00 AME 2413, 3A IME 2567. After SRL training, AIM 24 jumps to 16.7, AEME 25 to 13.3. Then they run RLVR reinforcement learning with verifiable rewards after SRL, and it explodes AMC. 2350, 5 AIME 2420, 0. 0 AIME 2510, 0. That's actually the highest open source result in the research right now, and the authors are crystal clear. The winning recipe is SRL first, then RLVR. It's not just math either. They also tested SRL on code reasoning with qwen 5 coder 7 billion instruct. They took 5,000 verified software engineering trajectories generated by Claude 3.7 Sonnet, broke them down into 134,000 stepwise examples, and trained on those on SWE Bench verified. The base model got 5. 8% in Oracle file edit mode, 3. 2 end-to-end. The SWE Gym 7 billion baseline hit 8, 4 and 4, 2. SRL blew past both 14, 8 and 8, 6. 6% roughly double the base model. So what's actually happening here? SRL reframes reasoning as action generation. The model isn't predicting the next token. It's deciding the next move. Every step it takes is evaluated so it can learn complex logic in tiny increments. Compared to old methods, it's night and day. Supervised fine-tuning tends to overfit long demonstrations while plain reinforcement learning collapses when no rollout is correct. SRL fixes both dense feedback, zero overfitting, and no need for perfect examples. And it's stupidly efficient. There's no giant reward model. It's all done with lightweight string-matching GPO-style objectives and small data sets that makes it ideal for open-source developers who don't have a cluster of H100s. The crazy part is how cleanly SRL fuses two worlds that were never supposed to work together. It starts off grounded, training the model to mimic experts using standard cross-entropy laws, then flips the switch and lets it explore on its own, rewarding it when it finds smarter reasoning. For small models, that's a game changer. Instead of throwing 400 billion parameters at a problem, Google's basically teaching a 7 billion model to think with precision, to reason, self-correct, and actually show its logic. Suddenly you don't need a data center to get deep reasoning. You just need better training. SRL makes tiny models act like heavyweight thinkers, and that shift is going to ripple through every corner of AI research. Now, while Google's research nerds were busy teaching small models how to think, another team over at DeepMind decided that wasn't enough. So, they went full mad scientist and built an AI that actually does science. Not helping with spreadsheet science, like publishing papers and solving decade-old mysteries science. They call it the AI co-scientist, and it's built on top of Gemini 2.0. But it's not a single model. It's a full team of agents, each with a scientific role. There's a generation agent that brainstorms new research ideas by debating them internally. A reflection agent that acts like a peer reviewer pointing out weaknesses. A ranking agent that uses an ELO-style tournament to pick the best hypothesis. Then an evolution agent that merges top ideas or explores weird combinations. And finally, a meta-review agent that watches everything and keeps improving the system over time. Is a scientist in the loop setup? Humans set the research goal and guide it through natural language feedback. But the heavy reasoning is done by the AI swarm. So how good is it? Let's start with the first experiment published in Advanced Science. The goal: find new drugs for liver fibrosis, a deadly disease caused by scarring in the liver. Human scientists have struggled for decades here because existing lab models don't mimic real liver behavior, and effective drugs are nearly non-existent. The team asked the AI to explore epigenomic mechanisms, chemical factors that regulate genes without changing DNA. They gave it one well-crafted prompt, specifying the problem and the methods, then stepped back. So, the AI dives into the scientific abyss, chews through thousands of papers, and casually spits out 3 drug ideas that could reverse liver fibrosis. HDAC inhibitors, DNMT1 inhibitors, and BRD4 inhibitors. Then, just to flex, it also tells the humans exactly how to test them. Like, yeah, go run some single-cell RNA sequencing while you're at it. The researchers tested all of this using human hepatic organoids, basically miniature livers grown from stem cells. These organoids can actually develop fibrosis when triggered with TGF-beta, so they're perfect for testing. And guess what? 2 of the AI's drug classes worked beautifully. HDAC and BRD4 inhibitors both reduced fibrosis. One of them, vorinostat, is already FDA approved as a cancer treatment. In this model, it didn't just stop scarring, it boosted the growth of healthy liver tissue. Gary Peltz from Stanford, one of the lead researchers, said he was shocked. When he checked PubMed, he found over 180,000 papers on liver fibrosis, but only 7 even mentioned vorinostat. 4 were irrelevant. 1 just had it in a table, and only 2 had ever tested it. The AI found the connection instantly. To be sure, Peltz tested 2 human-selected drug targets that had more literature support. Neither worked. The AI's picks outperformed both. Right now, his team is collecting more data to see if vorinostat can reverse established fibrosis. And they're already in talks with pharma groups about clinical testing. That alone would have been a headline, but Google didn't stop there. In a second study published in Cell, the same AI system tackled a totally different challenge. A decade-old biological mystery involving bacteria. Researchers at Imperial College London had spent more than 10 years studying something called CFP-CCIS, capsid-forming phage-inducible chromosomal islands. Basically, tiny genetic hitchhikers that hijack viruses or phages to move between bacteria. The problem: these things kept showing up in totally different species. Even though phages are picky little divas that usually infect only one type of host, the human team eventually discovered the secret mechanism. They called it tail piracy. These CFPIC eyes build their own DNA fill heads but no tails. Then they hijack tails from other phages, even across species, to form hybrid particles that inject their DNA into new hosts. The question was simple. Could the AI figure that out without seeing the answer? The researchers fed it only pre-discovery data and asked how CFPX could spread across species. The AI produced 5 ranked hypotheses. The top one, that CFPX achieved broad host range through capsid-tail interactions. That's basically the same mechanism, tail piracy, that humans had spent 10 years uncovering. The AI got there in days. When benchmarked against other top AI models, none came close to reproducing that reasoning. Thanks for watching and subscribe the channel.